Does anyone have any homework questions you want me to go over? Okay, well, let me finish, since I just put this up, let me finish the example that I started last time, and then I'll go back and do homework problems. Okay, we'll have plenty of time. It's just I already put these up here. About the test that you took last week, today is a week. It'd be nice if I could hand it back today, but I can't. Hopefully I'll hand it back on Wednesday. That's my plan. Okay. I could hand it back today, but it wouldn't be graded. So it wouldn't do much good. Okay. So this is the problem that we did last time, a three-dimensional statics problem. We have that big plate that's held by a ball and socket joint and two cables. And we got about, I don't know, half-ish way through. So the free body diagram for it looked like this. You can see each of the cables, we know the direction of that force. So they're represented with an arrow in the known direction and just a scalar variable. The ball and socket joint is a totally unknown force vector, so we don't know any of these three components. So that's represented with that force vector that's at that red dot that is where I chose the about point. And now this is where we are in the table, just going through all these calculations. So there's only, you can look on the free body diagram. There's 1, 2, 3 forces on the free body diagram. We have 3 forces in the table. So we just have the one to go. That's this force TB. Okay, so the row vector for TB from the about point to that point D, where that force is applied, is 2.5 meters in the positive x direction, and then nothing else. So 2.500. And now we have to think about the force vector, and that's a little more complicated. So what I'm going to do, it's the same thing I did for the force TA. I'm going to take the coordinates of B, subtract the coordinates of D. Then I'm going to take a unit vector in that direction and multiply it by the variable, okay, to represent that force. Anybody have any questions about that approach? Okay, what I didn't write down, I guess, is the coordinates. But so the force vector from TA. Okay, that's what we're doing now. So first I'm going to get a vector that goes from D to B. Okay, so I'm going to call that my vector U. And it's the destination point, 0, 1.5, negative 2. From D, like dog, to boy. Because you can see the direction of that force is going from dog to boy. So the coordinates of dog minus the coordinates of boy. No, the coordinates of boy minus the coordinates of dog, sorry. And so this vector that's in the correct direction, the same direction as the force, is negative 2.5, 1.5, negative 2. Yeah. In the last class, I think for B, 2 was positive on the C direction. B vector. Zero, y is 1.5. Well, it's because they're on opposite sides of the XY plane. You know, the points A and B are on opposite sides of the X. You see that? Okay, so that's a vector that's in the direction of the force. It's just not the right magnitude. So to make it the right magnitude, we're going to first take a unit vector in that direction, and then we're going to multiply it by the magnitude we want, which is TB. So the unit vector in that direction on Inspire or 89, there is a function, and anything else, it's pretty easy to write that function. The function on the Inspire or the 89 is called unit v. So this unit vector is negative 0.707, positive 0.424, negative 0.566. And so then finally the force vector is this multiplied by the variable TB, so negative 0.707 TB, positive 0.424 TB, negative 0.566 TB. Okay, so now I'll put this in here for the force vector. So negative 0.707 TB, positive 0.424 TB, negative 0.566 TB. One thing about this cross product is since everything is multiplied by TB, it's the same as just doing the cross product of those numbers and then multiplying the answer by TB. So that's a useful thing if you want to plug it into your calculator. So I'm going to cross 2.500 with negative 0.707, positive 0.424, negative 0.566, and we get 0 for x, 1.415 TB for y, and 1.06 TB for z. All right, so now I'm going to go to Newton's laws. The first one is Newton's second law, and it says that r vector, rx, ry, rz, plus 0, negative 490.5, 0, plus negative 0.816 TA, positive 0.408 TA, positive 0.408 TA, plus negative 0.707 TB, positive 0.424 TB, negative 0.566 TB is equal to zeros. And now we'll add up all the moments and set those equal to zero. So rotational Newton's second law. We have 0, 0, 0. I won't write that. Plus 0, 0, negative 613.125. Plus 0, negative 0.816 TA, positive 0.816 TA, plus 0, 1.415 TB, 1.06 TB. And these are equal to zeros. Okay, so we have the 6 equations that we expect from Newton's laws. How many variables do we have? Rx, Ry, and Rz is 3 variables. Then we have TA and TB. So that's 5 variables. Okay, so we have 6 equations, but 5 variables. That's going to be a problem. Look at those equations, though, and tell me if you notice anything about the 6 equations that we have there.
One of them just equals 0.
Exactly. So the x components of the moment equation just says 0 equals 0. So that's not really a real useful equation. Okay. And so all together, these come out to be 5 equations. And now this is something we can solve. So I'm going to go to the augmented matrix. We're going to have 5 rows, 1 for each of our equations. So there's equation 1, 2, 3, 4, 5. And we're going to have 6 columns. That's 1 for each variable and then 1 for the constants. I'll do these in the order Rx, Ry, Rz, TA, TB, and then the constant. So my first equation says Rx's we have 1. TAs we have negative 0.816. TBs we have negative 0.707. Everything else there is 0. Equation 2. Ry's we have 1. Skip the constant for now. We're going to put that on the other side of the equation. TAs we have 0.408. TBs we have 0.424. The constant, if you put it on the other side of the equation, that's positive 490.5. Then the Z equation, RZ's we have 1. TAs we have positive 0.408. TBs we have negative 0.566. and no constants. Then equation 4 is the y equation from the moments. TAs, we have negative 0.816. TBs, we have 1.415. Everything else is 0. The last equation, TAs, we have 0.816. TBs, we have 1.06. The constant on the other side is positive 613.125. Everything that's blank, and I got R is equal to 175.39. Did anyone else do this, by the way, just now? No.
I got something else.
Something else? What did you get for the first number?
I got 525.
Ooh, that's what I got last year. So I think that's right. I entered something in wrong. It's just so easy to enter something in wrong. Okay, so 529.9 about 210.1, negative 35.6, and then TA was at 430.2.
I got 429.56.
Yeah, that's just round off error. We just entered in. And then TB, you got about 247. Okay, so there it is. So even just a single three-dimensional body, you end up with somewhere right around 6 equations and 6 variables. It's kind of tedious, but conceptually it's the same as 2D really, as long as you just remember the definitions of the joints, what kind of loads the joints apply. Anybody have any questions about that one? Okay, so now that was the example we started last time. So let's take a bit and go through any homework problems people had from last time. 7? Anybody else have requests? 5? Yeah. 4. 4, 5, 7? Okay. 4, 5, 7, 8. Well, we probably won't get to all those, but let's see. So this is rigid body statics. Okay, so this is back to two-dimensional stuff. The nice thing about 2D is you only have 3 equations and 3 variables. So I'm going to start with a free body diagram.
Why don't you include the pulley?
Well, if you tried including the pulley, you would see that there's a fixed joint between the base of the pulley and the wall, and so it would add a bunch of other variables. And so I guess what we're trying to do is come up with something that has as few variables to solve for as possible. All right, so there's a pin joint here, and the rule for a 2D pin joint is that it just applies an unknown force vector in 2D. So I'll call this the vector RA. And then there's a roller to the right of it. That's like a frictionless contact. That applies a force that's perpendicular to the surface toward the chosen body. So that's straight up, and I'll call that RB. The mass of the beam is 100 kilograms. And that acts at the center of mass. And so 100 times 9.81 is 981. And then the only other place the surroundings contact the body is where the cable contacts it. So it's this direction. The tension is the same all the way along the cable, so this is just 500. Any questions about the free body diagram? So then we'll go rho, force, moment. Hey, I have a question. Did anyone email the dean? I'm just curious about, and if so, did she get back to you
About what?
about circuits for next semester?
I was going to send it today.
Today? Yeah. No one's heard back from her.
Gotta be proactive about it.
Yeah.
You've got a short time frame.
Very short time frame, yeah.
Oh, you teach circuits next semester?
I would not be teaching it, and to be honest, I don't really care, except if you guys care.
I care.
Yeah, Aaron cares.
Yeah.
Do it for Aaron. Everybody do it for Aaron. Okay, well, anyways, I was just curious. But if you're going to write to her, you better do it soon. I know that much. Okay, so I'm going to make this my about point. You can put it anywhere you want. So for RA, the rho vector is 0, 0. The force vector is RAX, RAY. Cross product is 0. Then I'll do the weight force. So that the rho vector is in the positive x direction, 0.5. So we got 0.50. The force vector is 0, negative 981. Cross product is negative 490.5. Then RB, that rho vector is 1, 0. Force vector is 0, RB. And then the last one is the 500 Newton force. That rho vector is negative 1.5, 0. And now we have to think about this force vector.
Isn't it just negative 1?
Yes, sorry. So now we have to think about this force vector. So a vector in the correct direction is, so x is negative 0.5, y is positive 0.75. Now a unit vector in that direction what am I doing? Is negative 0.555, positive 0.832. And so the force vector is 500 times negative 0.555, positive 0.832, and so that is negative 277.35, positive 416.025. I'll just call that 03. Cross product is negative 416.03. And now we'll go to Newton's second law. So it says RAX, RAY plus 0, negative 981 plus 0 RB plus negative 277.35, 416.03 is equal to zeros. And then the moment equation says 0 minus 490.5 plus RB minus 416.03 is equal to 0. And then that's three equations, three variables, and you can solve. Anybody want to see me go through the answers, which, you know?
Sorry, I just have a question for, like, finding the force vector for the 500.
Yeah.
I did it, like, by finding the angle,
Okay.
and I got the same answer, but I'm just curious, like, your unit vector, or no, before the unit vector,
Mhm.
where it says negative 0.5, those are the coordinates of the pulley or the point where it connects to the beam?
That is this vector. Sure. Any other questions about that one? Okay, then equation 5. Oh, good Lord. Who makes these problems? Okay, so let's see. We've seen this thing before in the vector review. You had to calculate all these components and stuff, bless you. So we know that let's see, the origin is at the center of mass. So I'm going to make that my about point, okay? Since it's already given us so many of these coordinates in that coordinate system. So I'm going to make the origin the about point. Then the reason for that is the row vector for each force is just the coordinates where the force acts. That's always true. So we don't have to do a bunch of subtractions and stuff to figure out row vectors if we make the origin the about point. Okay, well, I'm going to start with a free body diagram. And there's a weight force acting at the center of mass. This thing has a mass of 20 kilograms, so this is 196.2. There's a pin joint here, and in 2D, a pin joint is an unknown force vector.
If it's 3D, you go 3 ways, right?
Yep. We have-
Wouldn't a pin joint also have a moment if it was 2D?
This is 2D.
Yeah.
Oh, so the pin joint, yeah, it would have two couples, and so yeah, if it was a pin joint in 3D, you'd have to think about whether it provided thrust or not, and you'd have to think about whether there was another pin joint acting along the same axis, and then based on that, there could be two forces and two couples, or three forces and three couples, or just two forces, or just three forces. Okay, and then the last force is this cable force. I'll call that T. So that's the free body diagram. And now I'll make the table. I'll start with the weight force, since that is at, I chose that about point as the origin. So the row vector for the weight force is 0. The force is 0, negative 196.2. Cross product is 0. Now I'll go to the R vector. And the pin, so the row vector for R is 0.05, negative 0.2. Force vector is Rx, Ry. Cross product is this times this, minus this times this. Bless you. So 0.05 Ry plus 0.2 Rx. And those aren't vector components. That's all added together in the z component of a vector. Then the 400, that is acting at negative 0.5, positive 0.02. So that's the row vector. And it's horizontal to the left, so that's negative 400, 0. And the cross product is 8. And then last is the cable force. That attaches to the body at 0.6, 0.4. So the row vector is 0.6. It is this times this minus this times this, so it's a double negative, so it's positive. And then it says that that angle is 45 degrees that cable makes. So it's T times cosine and sine of 45 degrees. So this is 0.707 T, 0.707 T.
Oh, was it 0.8? Wasn't it 0.4?
Yes. I was writing and thinking and answering a question at the same time. Okay, so we got 0.6 times 0.707 minus 0.4 times 0.707. And so that is 0.141 T. Bless you. And now Newton's second law says 0, negative 196.2 plus Rx, Ry plus negative 400, 0 plus 0.707 T, 0.707 T is equal to zeros. And the moment equation says 0.05 Ry plus 0.2 Rx plus 8 plus 0.141 T is equal to 0. And we have 3 variables, 3 equations, so we can solve that. So remember, anytime the coordinates are easy to get, or given to you or whatever, you probably want to just make you can always choose any about point you want, but just to save a little work, you probably want to make your about point equal to the origin. Then your row vectors are just equal to the coordinates of the points.
Otherwise, isn't it easier to make the about point at R?
Yes,
Because then the moment of R is 0.
correct. Yep, that's right. And I just always want to reiterate, like in the big picture, it doesn't even matter. You just plug it into reduced row echelon form and solve it. But there are little tricks that can save you a little step here and there. Okay, so now what's next? Number 7. Okay, so this one has a couple different angles going on, and that's probably the trickiest thing about it. So a free body diagram. Let's see. The beam itself is at an angle of 45 degrees with the horizontal or the vertical. And the slot is 20 degrees from the vertical. So like we can think of this angle here is 20 degrees. And this angle here is 45 degrees.
Why do you pick that angle there?
What?
Like, why do you point it there?
Just that's what it says about the angles. So I'm just trying to make it clear what these angles are. Because it says that 20 is, it says that the slot, it makes a 20-degree angle with the vertical, not with the horizontal. Okay, so free body diagram. Here's the beam. This thing has a mass of 850 kilograms. Yeah, I know. I'll bet it doesn't even, I don't know. I'll bet it would have to be like a mile thick into the page. But anyways.
It only says it's 4 meters long,
Yeah.
so something really dense.
It would have to be like it could be a long plate extending into the page, you know what I mean? But I don't know. I'm skeptical. Okay, so 850 times 9.81 is 8338 0.5. And then there's a pin joint up here, so that's an unknown force vector. I'll call that RB. RBs. That could be such a good Arby's commercial. Do they still do the I'm thinking Arby's thing? And then, okay, I'm going to just draw this slot like this just to make the direction clear. And this force is perpendicular to this slot. Notice that there are two perpendicular directions you could draw to that slot, and either one is fine.
Wait, say that again?
I could draw, so for a pin and slot joint, it has to be perpendicular to the slot. Now, I could draw that force going up and to the right, or I could draw it down and to the left. Those are the two perpendicular directions, and either one of those is fine. You'll get the right answer either way in a pin and slot joint. Yep.
I'm trying to figure out which degrees of freedom are limited. So,
By a pin and slot joint?
yep.
Yeah. Okay. So, right, a pin and slot joint. So it can't go perpendicular to the slot. So there's definitely a force perpendicular to the slot. Okay. It can slide along the slot, so there's no other force component there. And it can rotate because that's a pin. And so what we get is just a single force vector with a known direction.
Does it go in? Is it?
It could go in that way or out that way.
Whichever direction we pick.
Right. And so that'll just come, it'll solve itself. That'll come out in your answer, just whether the answer comes out positive or negative. So I'm going to do it this way because that's in the first quadrant. I don't know. Doesn't matter which way though. And then I'll call this RA. So that's a complete free body diagram. And now I'm going to go to the table. I'll put the about point up here, I guess. What?
RB?
Yeah, I'll put the about point at Arby's. And so RB, the row vector is 0. The force is RBX, RBY. Cross product is 0. Then I'll do the weight force. So the row vector there is, the distance from that point B, the about point, to the middle is 2 meters because the whole thing is 4 meters long. So you can think of this as like 2 times cosine and sine of 225 degrees. So, well, this is 45 degrees. So like if you're going, oh my God, this thing is driving me crazy today. So here's your coordinate system. The vector we want is this, where this is 45. And so it would be, to go counterclockwise from the x-axis, it would be 90, 180, plus 45, so 225.
We just do cosine of negative 45?
Yeah. So This gives you negative 1.414, negative 1.414 for the row vector. The force vector is 0, negative 8338.5. The cross product is 11,790.6. And now I saved sort of the trickiest one for last. So now we're on to that force RA. So the row vector is just 4 times cosine and sine of 225. So that's not too bad. That is negative 2.828, negative 2.828. But now we have to think about the direction of that force. Okay, so here's a coordinate system. And I'm going to think about it like this. We know that the slot is 20 degrees from the vertical, like it's shown here. So I'm going to draw a vector. I'm going to draw a vector like this, where this angle is 20 degrees. And then the force that we want is 90 degrees from that. So I'm going to draw this one 90 degrees from the one I just drew. And now the angle, theta, if we're going counterclockwise from the x-axis, is we're going to go counterclockwise 90, counterclockwise another 20, then clockwise 90, so minus 90, and we end up with just an angle of 20 degrees.
Why do you go like 90 towards that side?
To what?
To that side, like why didn't you go from the point angle like to another one? For the like
To this?
no, also like on the 20 that one, like yeah, why didn't you make your 90-degree angle like to the left?
So
Like on
It
the
was
earth.
going
I
in
put the
opposite
arrow
direction.
from the 90 degrees the opposite direction that you have
Yeah.
right now.
I suppose that would be if you were to have the force vector pointing in the opposite direction, like if it was pushing on the pin rather than pushing.
Okay, so this vector, this black vector,
Yeah, she's saying what would happen if you put the arrow down to the left?
oh, like this?
No.
Oh, down to the left.
Yeah, like that, make it 90 that way.
Well, you can see the way that it's angled. I mean, that just wouldn't be the same line as that slot. I mean, just look at how the slot is positioned, you know?
So.
The slot goes up and to the left and down and to the right, so you can't you can't do it as if the slot was down and to the left. No.
Super easy.
Okay.
Professor.
Yeah.
I think what she's asking is like, you know how you said you could draw the force vector of the slot in different directions?
Yeah.
She's saying if like, what if you just do it the other direction? Like, how does it look like on that?
You can do that. Then this would just be the other way.
Yeah.
That's fine. But this one that represents the slot itself has to be either this way or that way.
Yeah, that one has to stay there, but
Yeah.
then from that one you move to the
This,
to 90.
yes, this can go either this way or that way. And if you put it this way, then you'd have 90 plus 20 plus another 90, and you'd be at 200.
Okay, yeah,
And that's perfectly fine.
okay.
but then that would be representing an arrow in this direction, so your free body diagram should have it in the opposite direction too.
But I would get the same answer.
Same answer in the end, yeah. Okay, so let's see. Let me just quick write this down and then we'll get out of here. So this is going to be, so that's 20 degrees, so it's going to be 0.939, no, 940 RA, 0.342 RA, cross product.
And that's the non, that's the,
So negative 2.828, negative 2.828, crossed with 0.342. And you get 1.691 RA. Okay, that's it for today.